Okay, so welcome everybody back. I see that a number of people have joined in the last few minutes, so we might as well start and not make people wait. So welcome everybody to this new edition of the Athena webinars. Today we have with us Elias Kammoun. It's for me a pleasure to introduce him. He's originally from Lebanon, where he got his PhD in Beirut his BSc in Beirut in 2012. Then he moved to the International School for Advanced Studies in Trieste, in Italy. He got his PhD there in 2019. Then he moved to the US, to the John Miller's group in the University of Michigan in Ann Arbor. Then in 2021, he joined the XIFU team at the AGAP in Toulouse. And I think he's now going to moving to Roma. Università di... Are you already there?
Yeah.
Università degli Studi Roma 3. He, as you will see, his research area is focused on high energy astrophysics and on the study of the closed environments of black holes and inactive galactic nuclei. And he's interested in studying the UV and optical continuum reverberation energy in accretion disks. So it's no surprise to anybody that the title of his talk is, as you can see there, studying the corona-accretion disk through thermal reverberation in multi-wavelength. So without further ado, I will let him start with his seminar.
Thank you, Francisco, for the introduction and for the invitation to give that webinar. So yeah, as Francisco said, I'll be talking about the connection between the X-ray corona and the accretion disk through thermal reverberation. This is a work that we've started in collaboration with Joseph Babadakis, Michal Dovchak, and Christos Panayotou since, well, now almost 5 years. So I'll start by breaking the title into pieces and to introduce briefly each of the elements of that title, and then dive more into details about what we're doing. So yeah, I'll be talking about the corona disk correlation or connection in AGN. Just to introduce very briefly AGN, which is practically one of the most luminous phenomena in the universe that are thought to be around at the centers of galaxies. In the center, we have the supermassive black hole that is accreting matter through what we thought it's an accretion disk emitting in the UV optical. And next to the accretion disk, in the vicinity of the black hole, we believe that there is the X-ray corona, a cloud of hot electrons that are responsible of the X-ray luminosity that we are seeing, which is very variable. Of course, in the unification scheme, the simplified scheme of AGN emission and AGN structure, we have also much more elements like the broadline regions responsible of the broadline UV and optical lines that we see. We have the narrow line region, and we have at almost the parsec level the molecular torus that is thought to obscure, to be in the plane of the AGN, obscuring part of the AGN. Of course, that's the majority of AGN, but also around 10% or so of AGN also show relativistic jets that emit in radio. So overall AGN, there's a variety of AGN, and each of these components in AGN will contribute to a part or more than a part of the electromagnetic spectrum going from radio up to the gamma rays, depending, of course, on how we look at the AGN and what are the components that are dominant. In my talk, I'll be more focusing on that very small region of the AGN, the most central region of the AGN, where we have the black hole at the center, the X-ray corona, and the accretion disk. Of course, this is an artist illustration of what's happening, but it's representative of what we believe the structure is. So I'll be talking about, as I mentioned, about the reverberation. Just to introduce reverberation slightly. So recently we know that we can take pictures of black holes with the Event Horizon Telescope, but this is quite hard to do. You know, we've done so far 2 black holes only, and it's time consuming, it's very expensive, and it's not that easy as a technique to extrapolate to all black holes and to resolve that much. However, luckily, we can reconstruct an image or map the different parts of an HN using what we call reverberation mapping. And that can be done across the full electromagnetic spectrum. So there are different types of reverberations. There's the X-ray reverberation, which probes so practically if something is variable, then we can see a variability, but this element of the HN will irradiate other parts of the HN that will respond to that variation. So if we look at different wavelength and different timescales, we can then probe different regions and reconstruct the map or the structure of the HN. So if we're looking in X-rays, we can do that to probe the innermost region of the AGN, so the X-ray corona and the innermost region of the accretion disk, and then we're talking about time delays or reverberation about hundreds of light seconds. If we look at the UV optical continuum reverberation, we go to larger time scales of about light days, and we are probing more the accretion disk, the structure of the accretion disk. Also in the UV optical, but looking at the broad lines, the broad emission lines, we can probe the broad line region at a time scale of few light weeks. And if we look in infrared, we can probe the dusty torus at a time scale of months to years. And there's a recent review by Kakat, Bentz, and Kara in 2021 that summarized very beautifully all these techniques and summarize where we stand and what are the main results of such techniques. In my talk, I'll be focusing on the second one, on the UV optical continuum reverberation and how we can use that to probe the structure, to understand what the black hole is doing, and learn more about how AGN are functioning. So what's the X-ray emission? What's its origin? How we have it? What's its shape? So just to simplify things, as I mentioned, we have the X-ray, the accretion disk. That is, if we break it down, simplifying it to annuli, we can say that each annulus of the accretion disk is emitting a black body radiation with a given temperature. So if we integrate over the full accretion disk, we will have a multi-temperature black body emission that's represented here. And that's speaking for AGN in the optical UV range. So this thermal emission we will get part of it as observers, but also some of that emission will go into the corona the X-ray corona that will inverse Comptonize this emission and bring it from the optical UV to the X-ray. So the X-ray spectrum is what we call the primary X-ray spectrum that we get is the direct coronal emission that can be approximated by a power law with a high energy cutoff. Of course, the parameters of the power law, let's say its photon index, its high energy cutoff, depend on the properties of the corona, of its the temperature of the electrons and the optical depth of the electrons, etc. But that's not the full story, because part of this X-ray emission will be emitted, say upward, or will be emitted because it's emitted isotropically. So we will get part of it, which is the power law here. But another part of the X-ray emission from the corona will irradiate back the accretion disk, and it will be reprocessed and re-emitted. That's what we call the reflection in X-rays. So we will get an additional component in the X-rays, as we see here, which is the reflection component, characterized by soft lines, characterized by the iron K line, and the Compton hump. Of course, by using the reflection, we can infer more about how the spin of the black hole is affecting this. We can measure the spin of the black hole. We can measure the structure of the corona, its height. We can measure the inclination. So by understanding this, by studying this reflection, we can infer a lot of information about the corona and the disk. So this is one of the first pieces of evidence about the corona and disk interaction. And observationally speaking, we have tons of evidence of such interaction, either using X-ray spectroscopy, where we can see the iron line, we can see the red wing of the line, we can see the Compton hump with NuSTAR as well, or using also time lags in X-rays, where we see that the variability in the region where that is dominated by the iron line, for example, in this case, it's delayed with respect to the continuum. So practically what's happening is that there is a variability in the continuum. The X-ray, the primary X-rays are variable. And after a certain time, a few hundred seconds, we see the disk responding to that variability. So we already know that the corona and the disk are interacting. We know that most likely the corona, there's the X-ray corona that is irradiating the accretion disk. So if that's true, so if the X-rays are illuminating the accretion disk and the X-rays, we know that they are variable. So practically we should expect that to see a correlation between the X-rays, the UV, and the optical as the corona is irradiating the accretion disk here, but of course with a certain delay. And this has been seen since the 90s now, almost 30 years now, even more. And even more, we're seeing it in the last few years. So these are the observations in 1992 by Ginga, where we see the X-rays variable in NGC 5548, and we see the light curves in the UV that are responding to this X-ray variability, and we see pretty strong correlation between the X-rays and the UV. This has been even more confirmed in the last years, and you can see now, you can appreciate now the quality of the data, how we went from practically this quality of light curves to this quality of light curves. And thanks to long monitoring in nearby AGN with HST, SWIFT, and other ground-based telescopes, now it's confirmed that in many of these AGN, we see a connection between the X-rays and an even stronger correlation between the UV and optical, where we see also a time lag. We see a time delay between the different bands, so between the different light curves. If we take that peak, see, as we go to longer wavelength, the peak is moving and it's becoming broader and broader. So there is an evidence of time lags that increase with wavelength, and this practically cannot be explained by a intrinsic changes in the disk due to accretion rate or propagation of fluctuations, because what we believe is that if there's any fluctuation, it should propagate inward. This will give an opposite effect. It will not give a time lag that is increasing with wavelength. So the most plausible explanation for that is that it's due to a response of the disk to the X-ray illumination, to the X-ray variability. So if we have the X-ray that are flashing here, after a certain time, we will see the flash, or we'll see the response of the disk to that flash, to that variability. So we have the X-ray flashing, we wait a bit, and then we see the echo in the accretion disk. So what did we learn from all this monitoring? And here I'm citing really just a few of the works that have been dealing with that, and we have now amazing data sets. And so practically the simplified image of that is that we have the corona here that is irradiating the disk, and then the X-ray photons will reach first this part and this part and then this part. And if we assume that the time lag is practically the light crossing time, so we can estimate the radius at each part of the disk, and we can practically, if we simplify things using standard accretion disk models, the Shakura scenario model. So we can attribute to each radius a certain temperature, and assuming that each radius will emit a black body. So the temperature is proportional to 1 over lambda, 1 over the wavelength. Then by putting all together, we can estimate the time lag to be proportional to mass times the accretion rate to the power 1/3 and times lambda to the power 4/3. And practically, these are the observations here. So these are the observations of NGC 5548. These are the time lags as a function of wavelength. And we see that the data points are clear that there is an increase in the time lags and the time delays as we increase the wavelength. So if we adopt this simplified scheme and we want to fit knowing the mass, knowing the accretion rate, and for that source, for NGC 5548, the accretion rate is estimated to be around 0.05, so 5% of the Eddington limit. We see that we cannot practically model correctly the time lags. This is accretion rate of 0.1, of 1, and this is of 10. So we need a much higher accretion rate to model that. So the first conclusions from this long monitoring, here I'm showing only 5548, but for most of the sources that have been monitored, we see more or less the same behavior. So we see that the shape of the time lags agrees with what's the standard disk. So with the 4/3 lambda to the power 4 of 3 that is thought to be, but not the amplitude. We need much more amplitude. So practically many people were suggesting that could it be that the accretion disks are larger than expected, or in other terms, that the accretion rates are much higher? That's one very important question because it questions all the known physics of AGN, and maybe that we are missing something. And the second very important result that came out of these monitoring campaigns is that if we look at the UV X-ray correlation and at the UV optical correlation, we see a very strong UV optical correlation. Here I show the correlation coefficients for around 10 AGN. We see that it's very close to 1, while the UV to X-ray correlation is much smaller. It's very moderate, so it's always below the UV optical correlation. And if we believe that the thermal reverberation is a correct model, then how can this happen? How can the X-ray drive the UV optical variability while we see that the correlation between the UV and the X-ray is very moderate? So these are two important questions that I'll try to answer during that talk. So for that reason, we've been, and what I'll be explaining later and showing later, we tried to revise the thermal reverberation. So you can perceive it as a new model, but it's not very new. It's practically just re-looking at this model in order to model the time lags. That was our first aim, but we, as you will see, we went much beyond modeling the time lags. So if we estimate in the standard model, the simplified standard model, the time lags should depend on the black hole mass and the accretion rate. But things are much more complicated than that, because we have to take into consideration the luminosity, we have to take into consideration the inclination and the properties of the system. And of course, we should not forget the presence of the black hole. So we have simple and general relativity effects that are quite important, and that will affect the propagation of light from the corona to the observer or the corona to the disk, etc. And if we build on the knowledge that we've accumulated throughout the years from the disk reflection and from the X-ray reflection, we can learn much more and combine all this together to see what the thermal reverberation gives us if we implement all the effects. So the model setup is quite simple. We assume a lamppost geometry. It's a model that we know it's a simplification of what's happening by assuming that the corona is a point source located on the rotation axis of the black hole, but we have to start from a certain point. So we assume that there's the black hole spinning, so we take into consideration the spin of the black hole, the corona having a certain luminosity located at a certain height, and then we can probe the photons going to the observer, the photons going to the disk, and from the disk to the observer by taking full GR into consideration. So if we know how much photons are emitted by the corona, we can know how much photons will be incident. We know from reflection models how much will be reflected in the X-rays, and then we can estimate the difference to be absorbed by the disk. So what's happening is that the X-rays from the corona are emitted, part will go to the observer, part will go to the disk, a part will be reflected, this is the reflected flux, and another part will be absorbed by the disk. The disk will be heated, and then the temperature of the disk at a certain radius at a given time will increase. So from that difference between incident and reflection, we can get the so-called new temperature of the disk, or the heated temperature. And that will tell us practically how the disk is responding to the corona variation, to the X-ray variation. We can estimate what's called the disk response function, so practically how the disk is responding to the X-ray variability. And from that, we can estimate afterwards the total flux integrated over the full disk and integrated over time, or at a certain time. And so practically these two quantities are the main quantities that will allow us to go deeper into our studies. I will start by analyzing more the disk response, and then we will get to the total flux later on. So the disk response, what do we do? We send an X-ray flash at a certain time, let's call it T0, and we wait. And then we see how the disk will emit in response to that X-ray flash. And the UV and optical, we can define any wavelength that we want. That's how we construct the response function. And we estimate the centroid of this response function, what we call the average time lag. And what did we see just by analyzing the simplified picture of time of responses? This is the response in the green is the response in optical. This is at short, the blue is at shorter wavelength in the UV. So the first conclusion, just by looking at that simplified picture, is that, which is based on real simulations, is that all the response functions at all wavelengths, they start simultaneously. There's no delay in the start time. So all of them start simultaneously, which is a very natural implication of the fact that each radius from the disk is emitting a thermal emission. So it will be emitting at all wavelengths. So if we are seeing that a photon from a certain radius, we will see this radius in UV, in optical, and mid-infrared, etc. So we'll see across the full spectrum the start of the response of the disk from that point. That's why all of them are starting at the same time. The second conclusion that we can see is that the response functions for longer wavelength for optical are much broader than the response in the UV, so in short wavelengths, because as the time passes, we see the X-rays will irradiate further out region of the accretion disk that we'll start to see, and that are colder, so will contribute more to the optical than the UV. So that's why we see the response broader in the optical than the UV, which will naturally explain that the centroid of that response is larger in the optical than the UV. So it's increasing with wavelength. So practically, we go from a picture where each radius will emit in approximately one wavelength to that each radius is emitting at all wavelengths at the same time. But then as we go further, we have more emission in the long wavelength than in the short wavelength. These results were summarized in different papers that we've been publishing since 2019, dealing mainly with time lags. And by analyzing the responses as function of different properties of the system, so like the mass, the height, the accretion rate, the color correction of the disk, the X-ray luminosity, etc., we could reconstruct a rather simple, maybe it does not look that simple, but a simple analytic prescription where we can see the correlation of the time lags, the function of the height, of the mass of the black hole, of the accretion rate, and the X-ray luminosities, and the color correction. We've done that exercise for two spin values only, for a non-spinning black hole and a maximally spinning black hole. And using this rather simple approximation, we could fit the time lags in practically almost all AGN. So here I'm showing 7 AGN, but it has been applied also for other sources. And we show that it does work perfectly. And from that, we can, if let's say we know the mass, we can fix it. We know the X-ray luminosity from observations, we can fix them. And then we can fit for the other parameter if we fix also the color correction, for example. And from that, we can get constraints on the accretion rate, on the height of the corona. So we can put some constraints. Of course, in some cases, or many of the cases, the constraints are not that strong because of the data quality and of the sources, etc. But we can get an estimate, for example, whether this model works or not, and what's the approximate, let's say, height or accretion rate in a given source. Of course, if we combine it with other information, say, for example, if we say the accretion rate should be in that order of magnitude, for example, we can maybe rule out one of the spins, like in Markarian 142, by saying that the accretion rate should be high or in that order, so maybe a spin 0 does not work, or vice versa. But more recently, in a paper in 2023, so that has been published a month or so ago, we've explored that more into details. And we have now a more recent model that's publicly available that allows to simulate and fit the time lags in a much more flexible way and having more options with respect to the analytic approximations. So here you can run the code, you can get the responses for different heights, mass, accretion rates without going through the simple analytic expression that we have. But also, one very important addition that we have in this newest release is that we can now connect also the X-ray luminosity to the disk. So we have two options. Either we assume that the X-rays are heated or powered by the accretion flow. We don't know how exactly, but let's say the power of the X-rays is coming from the disk. So this is given that power. So what we call the internal power, or we can disconnect the two, and then we have another unknown process that could heat the corona, but it's not coming from the accretion disk itself. It could be the black hole, for example. So we have these two more options as well. And by applying this and assuming now that the corona and the disk are connected, and so the power of the X-ray is coming from the disk, we performed fits for different sources. Here I'm showing 4 sources. I know that's very small, but that's on purpose made very small, just to tell you that by assuming the known mass and accretion rates, we can fit for all the sources perfectly the time lags. And as I said before, the time lags were not, the model was not working by assuming a certain accretion rate. Now what we can say is that the model is working too well. We don't want it to be that good. You know, it's fitting by just fixing the accretion rate to what the accretion rate should be. It works for different combinations of spins, of heights, of color corrections, of powers. So the first conclusion that we can say here, that's my first conclusion, is that an X-ray illuminated standard disk, assuming standard masses, standard accretion rates, does explain perfectly the UV optical continuum time lags. And that's very important. So that's a first test that the model of thermal reverberation passed. But then we can go and we should go beyond that. And from now on, I'll be focusing on the case of NGC 5548 to show that this model actually works. We chose NGC 5548 because it's the first source to be intensively monitored with HST, SWIFT in XRT and UVolt, and ground-based telescope over more than 5 months. So arguably, this is the best data set that one can ever have. Of course, now there are new sources like Mercurian 817 having also these long intense monitoring and many other sources, but we started with that. And hopefully we'll extend to more sources. So this source, but these are the different light curves that we are seeing from HST up to the SDSS-Z band at around 9,000 angstrom. You can see that there is time delay as we saw before. This source show a low or moderate X-ray to UV optical correlation. So it's one of the best sources where we can ask, are the X-rays really driving the UV optical variability? And thus test our model. And as I mentioned before, so it's one of the sources where a standard accretion rate and the standard accretion disk could not fit well if we simplify things. But as I showed before, and that now we can eliminate that. But let's keep it in mind. So we are asking ourselves, is thermal reverberation a viable model to explain all this variability in that source? So as I mentioned before, if we use the external power and the simple analytic expression, we can fit very well the time delays in that source. We can constrain the height, somehow constrain the height and the accretion rate, so we can put some constraints. But what we did in Panagiotto et al. 2020 and 2022, that we went the first step beyond the time lags. And if we assume now, let's assume that the model is correct. So within that framework, within that context, if the X-rays are variable, then and we have the responses, we can estimate the power spectra in the UV and in optical. So we're assuming that this is the power spectrum of the X-rays. This is fitted by fitting the observed ones. We assume that this is the driving power spectrum, and then we ask ourselves how this will be propagating into the UV and X-rays. And using that simple model, practically, we could constrain and we could fit very well the power spectra in the UV and in optical, and combine all of that to the time lag spectra, and then getting more constraints, as stronger constraints on the height and the accretion rate for this source. Of course, these were applied for spin 0 and spin 1 only, but it does work. So what this is telling us that we could explain the UV optical variability just by assuming that the X-rays are variable. So the X-rays are the driving process through thermal reverberation. And that's another important test that the model passed. We went even beyond that. And then, so if we can explain the lags, we can explain the variability, then the last question to be asked, what about the spectra? What about the energetics? And that's a very important question for any model, because if we can explain the relative variability, that's quite good, but we need to see if that model could explain and could measure properly the energetics that are in the corona, in the disk, and all that connection. So in Dovchak et al. 2022, we presented the model called KINSAT, which is based on the same physics, but that can be used to fit the broadband SED from the optical to UV to X-rays, assuming thermal reverberation. The code is publicly available and can be used easily in XSpec. And here, let's go back to the second equation that I showed before, which is the total flux, because that's a very important and a very tricky quantity to be computed. So assuming thermal reverberation, it's important to keep in mind that there are delays. What does that mean? So simultaneous observations may be misleading, because what's happening is that if we send an X-ray photon at time t0, we start observing in UV and optical at much longer times. And as you can see, the response functions are short in UV, more extended in optical and infrared. So if we are looking today, we are seeing what the source is doing today in UV or in optical. Practically, what the source is doing is responding to what the X-ray source did half a day or even more than 1 day before. But if we're looking at the I band, so here the time lags are almost a day. So practically in that band, the UV emission today is responding to what the X-ray did yesterday. But we are observing simultaneously. So we are observing the X-rays today. We are observing the UV optical today, but they are not corresponding to the same thing, because in response to what the X-ray are doing today, we have to observe tomorrow, for example, in optical. So that's tricky. So that's why we're integrating in the past practically. So there are two solutions. What can we do? We cannot observe each wavelength at a certain time and then cross-match. It will be completely awkward to do that and very complicated. So there are two solutions. Either we observe over very long time scales and we integrate over all of this. So practically we average over this. And what we say is that we are just looking at the average behavior of the source, or we have to construct very carefully a time-resolved SED by saying that what we are observing today in the UV optical is corresponding to what the X-rays have been doing for 1 day or for 2 days or 1.5 days. And that's very, very tricky, but we'll come back to this later. So first, we went one step back and we say, okay, what do we know about NGC 5548? We know that the model can fit the time lags. Fine. What are the parameters that the best fit parameters? And as you can see, it can fit for spin 0, for a moderate spin, or for a very high spin, for different ACO, for different fraction of the power going to the corona. Of course, all the time, assuming constant black hole mass and accretion rate that are 5%, I think. There I'm showing again the time lag as a function of wavelength, but it's on purpose that I put all these models in the same color. And as you can see, all of them fit very well the time lags. And you cannot discern by just looking at this or by discerning them statistically, because they are all very good. So we said the first step and the easiest step is to look at the SED. Can the SED tell us more about which parameters work better than other parameters? So we looked at the time average SED and we fit using KINSAT, the UV, optical, and X-rays, the time average. And from that, we could get rid of, for example, the maximally spinning black hole. So there are two spins that survive, which are the spin 0 and spin 0.7, and only for an F-call of 1.7. This is from a work that is really almost submitted. We've been working on that for some time now, and we are very close to submission. So this is a first test that also passed in terms of SED. It's the time average, and we could shrink the parameter space even more. Then comes to this, the second solution, which is more tricky. So as I said, constructing a time-resolved SED is a very tricky business. But we dared and we attempted to do that. So we looked at the light curve. This is in X-rays, this is in UV. And we said that, okay, fine, let's choose the UV bands. So these are the shortest wavelengths. In this case, the response should be on average less than 1.5 days. And we constructed 15 spectral energy distributions from these few hundred days. So what we said is that we take the UV at this point, we take this observation, and we integrate back the X-rays for 1.3, almost 1.5 days. Similar for here, similar for that. So practically what we are trying to mimic is that within uncertainties, how much the response is long in these wavelengths, so how much we should integrate back in time. So we start from this time and we integrate the X-rays back for 1 day or 1.5 days. We constructed 15 of these SEDs, and we've tried to fit them with KINSAT, assuming one, that the X-ray is powered by the accretion disk. So we have a connection between the disk and the corona. Second is that the accretion rate is constant. And third, that obviously the X-ray source is variable. So in other terms, what I want to say is that what we assumed is that any variability that can be seen in the UV should be coming from the responding to the X-rays. So all the UV optical variability is only due to the thermal reverberation process, to the connection between the X-ray and the UV, assuming that the X-rays are the driving mechanism. And surprisingly, we could fit the 15 SED very well. And what's even better news for us is that we could get rid of the other spin, and only one spin survived, which is the non-spinning black hole. So we could fit perfectly, assuming constant accretion rate and a spin 0, all the 15 SEDs. What is this telling us? This is a very important thing to explore, because if you remember, this was a source where the X-ray and the UV were moderately correlated. So it's an important question to ask if really we can recover practically the UV and the X-ray variability simultaneously. And that's what we did. Here I'm showing the UV X-ray light curve similar to before. This is one of the UV light curves. In black, there are the observations. These are in X-ray, the average. In UV, the observation at a given day. And the model is the diamonds. And you can see that we can perfectly recover all the variability, even the strong variability that can be seen here when the X-ray dropped and then go back. We can recover it. And in the same time, if you look at this, for example, you see the X-rays are going up, then down, then up, while the UV are just going up and then after a while going down. So we could recover all this variability in the X-rays and in the UV just by assuming X-ray illumination and a constant accretion. Of course, we want to know more about the physics and why this is happening and how to explain that. So in the model, that the only three parameters of the system that were variable were the height, the photon index of the X-rays, and the transferred power. And as we can see here, that all three parameters vary quite a lot during these observations. And so practically, each of these parameters alone will affect the observed flux in a certain way. But by combining all of these three together, we could perfectly reconstruct the moderate observed correlation between the X-ray and UV. So it's the combination of change in height of the source, change in gamma, which could be practically related to a change in the temperature, so a change in the intrinsic properties of the source, of the X-ray source, and change in the power that's given to the corona, change in the heating power. So the heating and the cooling are changing, the temperature is changing, and the corona is not static, it's quite dynamic. We could reconstruct all the X-ray UV optical variability in that source. So the conclusions, number two, I'm not introducing any new physical model. It's a very simple model, just known physics, just by doing them more carefully, taking all the properties of the system and all the complications of the system into consideration. So assuming this X-ray illuminated accretion disks, we could explain the time lags in many sources. We could explain the UV optical power spectra in NGC 5548, and hopefully we're extending it to more sources. We could explain the time average X-ray UV optical SED for NGC 5548, and we're working on other sources. 4, we could explain the X-ray UV spectral variability of NGC 5548, and even we could explain using that model in Pangiotto 2022. Christos could explain the moderate correlation between the X-rays and the UV, which is also in agreement with what we found in NGC 5548. And 5th, which I could not show here because we don't have enough time, we could even, by assuming that model, explain the disk size problem in gravitationally lensed quasars. But that's not all, because there is some part that I didn't mention before, and that's important. Another important test for our model is, what about the sources where we do not see a correlation between the X-rays and the UV? So there are 3 unabsorbed sources, and I stress on unabsorbed because this is a very important aspect, because when absorption comes into the game, things will become much more complicated. So if we look at sources that are not absorbed, you can see that some of them, here I'm showing 3, and I'm not sure if there is more, but these are the strongest cases where we do not see. We look at the X-rays, we look at the UV, there's no correlation. In IRIS 1322-4. If you look at 21H0707, similar thing. And more recently in Markarian 1044, the same thing. So what's happening? And is the corona eliminating or not, or what's happening in these sources? Surprisingly, if we look at these 3 sources, if we look at their X-ray spectra, see that all these 3 sources have a quite strong reflection features. So what does that mean? So we are now in the beginning of that investigation, but this is a very important thing, because what we try to do here, and this is very preliminary, is just to vary the height of the source and to see how the thermal reverberation fraction, so practically the amount of thermal reverberation over the total flux in the UV optical, goes with height, and how the reflection fraction, so the reflection flux over the total flux, changes with height. And what we see is very important, because as the height increases, we see that, so going from blue to red, we see that the thermal reverberation fraction increases for spin 0 and a maximally spinning black hole, reaching around almost 75% for large height, while the opposite is happening when for the reflection fraction. So we see that as we go to larger height, the reflection fraction goes down. So these are sources that are reflection dominated, Iris and 1H and Markarian. So practically, we believe that we are in that regime of very high reflection fraction. So in the optical UV, we have very low thermal reverberation fraction. So if it's the thermal reverberation is 10 or 20%, and even if that is variable, it's very hard to detect with observations. So that's why most likely we are not able to see the correlation in these sources. And that's very important. And as I mentioned, this is still under investigation, but so far things are very promising. Which brings me to my third conclusion and a very important thing to say in the ACO webinar. Because, yeah, this is an Athena webinar, so, and I've been talking all the time about optical UV, but what about the X-ray? What about Athena? So from what I said, all the things that I said before, what we can say is that practically using thermal reverberation or X-ray reflection, we are looking at the same things. We are measuring the spins, we are looking at the accretion rates, we are looking at the properties of the X-ray corona. So practically, we are looking at the same systems, at the same parameter space, but we're using different methods, different wavelengths, and different timescales. And Athena and even new Athena and what's called now new Athena will provide very important constraints on the spin, on the geometry, on the corona disconnection. So the two techniques, the thermal reverberation technique and the X-ray reflection and the X-ray spectra technique are very complementary. And we can use one result for the other, and even with a strong constraint that could be done with Athena for the spins, for example, as shown in Variant Capi 2019. We can practically, for a given source, measure its spin, and then we know that the spin is fixed. It's not changing in these timescales, so we can fix the spin. And any viable model should explain the X-ray properties, the X-ray spectra, and the spins coming from the X-rays in the UV and optical to see what's happening. So there is a connection between both, and obviously, these are simulations for the WFI from Zogby 2019 for time lags in the X-rays. I'm not sure if there's any similar analysis for the XIFU, but with Athena and hopefully with new Athena also, we will be able to distinguish between different geometries of the corona. And this also will have a very huge impact on what the thermal reverberation will be doing. A point source will not be, so the disk will not be responding to a point source like it will be as responding to an extended vertically or horizontally corona. So there are more and more things to be done by cross-matching these two techniques. And I'm sure that a lot of exciting physics can be explored in the future, in the near future with CRISM, and hopefully in a few more years with new Athena. And I stop here. Thank you very much.
Okay, thank you, Elias. I'm really hoping that we can explore that exciting physics in a few years.
Hopefully.
So, are there any questions about this exciting physics? Just raise your hands and we should. There is a question here. Let's see. Can we allow this person to talk? There he is. Silvia, do you know how to? Okay, so you can talk now, Anatoly, please.
Yes, okay. Thank you very much for this, for such a great presentation. My question is, the Lampos corona approximation is more understandable or more or less clear for nuclei with jets, when the corona can be the base of the jet or something like this, as you show for NGC 5548. What about sources without jets? Is the use of the Lampos corona approximation justified in such cases? Thank you.
That's a very important, this is, I think, one of the exciting physics that we'll be exploring. So, so far, we don't have a clear answer, but because we don't assume We don't assume that the corona is due to jet or no. Obviously, there are different models to explain also non-jetted AGN. For example, if we look at the Ghisalini et al. 2004, where they assume that in radio quiet or non-jetted AGN, the corona could be a failed jet, which may be still similar, but we don't know. So what let's say the lamppost geometry is just a simplification. And we did one of the tests in the Dovchak et al. 2022 paper, the KINSAT paper, where we looked at the approximation, how the 3D spherical corona could compare, which is not very far from a lamppost. And we found that this is more or less similar. For different sources, we could explain, you see here, in the past, for different sources, we could explain the time lags. Now, what the corona could be doing for non-jetted, or we don't actually, I cannot tell now. It can be working, it can be not working, and that will be even more exciting if we can distinguish between the two geometries, saying that we have one geometry for AGN with jets or launching jets, one for another one. It's something to be tested. It will be even more exciting when the model breaks, because this will tell us why it's breaking, why it's not working, and what could we learn. So it's worth investigating, I believe.
Any other questions? I have a very naive one, and is that I guess you said something about this, but I may have missed it. The X-rays are supposed to be upscattering of Dix photons to start with, right? The UV illuminates the corona, and then the corona upscatters them into X-rays. And
yes,
do you take that into account in your model somehow? Or?
Yes. So in the model, we have the power and we have the photons coming from the disk. We know what's the disk, the bare disk without illumination, and this goes into the corona. And of course, using simplifications of, but the energetics are the same, so we have conservation of energy between what's coming into the corona and what's going out. We approximate the corona by a power law. We don't use a Comptonization model for the corona emission, but that's why we have the gamma factor and the cutoff free in some cases, but that's the first approximation. Now, of course, we can change it back to a more Comptonized. It should be relatively simple, maybe. But yeah, so in terms of energetics, it's conserved. It's taken into consideration how much we have, and this sets the low energy cutoff of the X-rays. That's also taken into consideration based on the accretion disk power.
Okay, so and I guess that a flare. Okay, you are sort of assuming that the changes are in the corona and not in the disk because the time scales or something.
Yeah, we're assuming that mainly. So we're testing the model where the changes are mainly due to the corona. So the disk is not changing. It's only changing by responding to what the corona is doing.
Okay. Thank you. Any other questions? I can't see any. Okay. Well, I have another curiosity.
Sure.
now that we are on it, is that you said that you have the corona and this lamppost geometry in lower heights, then you have lower reverberation.
Yes.
Why is that physically? What's happening there?
So practically here, most of the illumination will be concentrated in the lower parts. So so we'll have most of the contribution going to the X-rays. So the reflection is very high. So if you remember, we have how we define the flux and the reverberation is the difference between the incident and the reflection. So if you increase the reflection fraction, because most of the X-rays will be illuminating the inner parts of the disk, and we get high ionization and a lot of reflection, so what's left for the disk to absorb is very minimal.
Right. It's not thermal. Okay, you don't use it for thermal energy.
Yes.
Okay. Okay, thank you.
Thank you.
Okay, any other questions? I can't see any in Q&A or in the participant list. So I guess we can be finishing now. So just thank you, Elias, again for your and the questions from the audience. And that's before we leave, just remind you that there is another exciting webinar coming out on the 16th of November by Monica Colpi on electromagnetic counterparts of LISA massive black hole mergers, the next challenge. So hoping to see you all there. Have a nice day and have a nice week.
Thank you.
All right.
Bye.